Sudah. Tes. Excellencies, ladies and gentlemen, very good morning. Welcome to SSGS 2-day seminar and workshop with the big theme of high accuracy, RTK and MADOCA PPP Global Navigation Satellite System GNSS Receiver. School of Strategic and Global Studies Universitas Indonesia, in collaboration with the University of Tokyo and Tokyo University of Marine Science and Technology TUMSAT, Japan present this event to all participants here, live in Jakarta and streaming in YouTube. It's a platform and discourse among potential partners and stakeholders in GNSS technology, development and application, and responding to strategic and global social and environmental issues. I am Cindy. It is a great honor for me to be the master of ceremony of this event. We are pleased to welcome the Excellency Atur Subroto PhD, Director of SSGS Universitas Indonesia. We present our honorable speakers and facilitators. Slide, please. Dr. Dinesh Manandar, Center for Spatial Information Science, University of Tokyo. Mr. Kaito Kobayashi, TUMSAT University. Mr. Wataru Yanagisawa, TUMSAT University. Dr. Lin Yola, School of Strategic and Global Studies, Universitas Indonesia. Mr. Garin Nandito, School of Strategic and Global Studies, Universitas Indonesia. And of course, we are proud to welcome our participants from multidiscipline backgrounds, UE faculties, School of Environmental Science, Faculty of Engineering, Faculty of Science, Faculty of Computer Science, DRRC UE. Cabinet Office of Japan and representation from by Entity Data Corporation, BRIN, BNPB, BIG, BMKG, MAPIN, ASPI, BPS, Dinas Cipta Karya, Tata Ruang dan Pertanahan Provinsi DKI Jakarta, BPBD DKI Jakarta, Bapeda DKI Jakarta, Penanaman Modal dan Pelayanan Terpadu Satu Pintu DKI Jakarta. Now, we present National Anthem of Indonesia. Please rise. Audience, kindly be seated. Thank you. Now, we invited Director of SSGS UI Ator Subroto, PhD, to deliver his welcome remark. Bapak Ator, please, the floor is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. A very good morning. Honorable partner, Dr. Dines Munandar, University of Tokyo, Professor Kubo, Professor Nobuaki Kubo, Tokyo University of Marine Science and Technology, Mr. Kaito Kohayashi, Tokyo University of Marine Science and Technology, Mr. Wataru Yanagisawa, Tokyo University of Marine Science of Technology, and distinguished respective participants from UI and other strategic partner of SSCS, Universitas Indonesia, that I cannot mention one by one. Thank you for coming. Ladies and gentlemen, I would like to welcome you all to this GNSS seminar and workshop, High Accuracy RTK and MADOCA PPP, Global Navigation Satellite System, GNSS receiver. The School of Stratejik and Global Studies, Universitas Indonesia, or SSCS UI, in collaboration with the University of Tokyo and Tokyo University of Marine Science and Technology, Japan, presents this International Global Navigation Satellite System GNSS seminar and hands-on workshop to introduce the introduction and technology application of GNSS for multi-stakeholders, including decision makers, private, and researchers. This year, our GNSS seminar consists of today's program with 3 topics: Introduction to GNSS for beginners, GNS application for urban environments, GNS technology development, and GNS application in Indonesia. The workshop introduces the real-time kinematic or RTK and MADOCA, precise point positioning, PPP, as an advanced development of GNSS technology. With these compact seminar topics and the hands-on, we hope that the knowledge updates and development of GNSS could strengthen our methodology in strategic and global studies, especially on the spatial and technological based approach. Today, we are honored to be with distinguished guests and participants. We also expect to further possible collaboration with range of institutions to work on the possible area in the future. To our close partner, the University of Tokyo and TUMSAT University, it is our high appreciation to welcome you again in our campus and sharing your latest updates on GNSS technology. Last but not least, to our SSGS staff and students, thank you for the great work in housing this seminar. With this, I officially open today's event. Please enjoy and thank you. A very good morning. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you, Bapak Ator, for the warm remarks. We also kindly ask Dr. Ator to present token of appreciation to our partners from University of Tokyo and TUMSAT University. Dr. Dines Manandar and Professor Nobuoki Kubo, we pleased to invite you to the stage for receiving the token of appreciation. Sorry. And to all participants, let's take a group of photo with the Excellency. Please, Dr. Dinesh Manandar, can you please come to the front again? We take a picture one more time with all participants. All participants, please gather to the front. Okay, now we move to our main agenda today, the seminar of GNSS. For this, we kindly invite Dr. Linyola to chair the session. Dr. Linyola is a lecturer of School of Strategic and Global Studies, Universitas Indonesia. She has a strong academic and professional background in urban, energy, and technology innovation. Please welcome Ibu Linyola.
All right, thank you very much, Cindy. Very good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. Yeah, I'm Lin Yola. Let me chair these sessions for day one program that we give the title of High Accuracy RTK and MADOCA PPP Global Navigation Satellite System Receivers. And of course, we have 2 days program, a very long one, today and tomorrow. But tomorrow we will have the hands-on program in Depok campus, in our beautiful campus. But thank you very much, first of all, everyone to attend these programs. I think there are around 12 or 13 institutions register for this event, sending the representative from each of the institutions. And we have some students as well following this event, especially for the hands-on tomorrow. And for today, we have 3 talks with the different topics. The first one is introductions to GNSS for beginners. So I think for some of you that are maybe having zero knowledge about GNSS can also follow this program and relate to what are we going to talk about for these 2-day sessions. And the second one is GNSS technology development. GNSS technology development. So for this one, maybe for some of you that are interested to develop the receivers and so on so far. I think some of you are from BRIN and requested also these topics. So this is also a suitable topic for you. And the third one is the applications or the examples of the GNSS applications in some areas. And the last one is the GNSS applications in Indonesia. We are going to share the applications of GNSS that we have doing in our school in SSGS Universitas Indonesia. And of course, the last sessions for today, we are going to have the Q&A sessions or discussions. So we are all welcome to give any questions or any discussions with the speakers. And of course, for tomorrow, we continue with the hands-on or the practical part of the topic that we are going to talk about today. So again, thank you very much for the speakers. Let me invite the three speakers that are going to speak today. Of course, we will continue again tomorrow for the another two speakers. Let me invite Professor Nabuoki Kubo to come to the stage. Yeah, I invite you to come to the stage. He's the professor with the GNSS experts from TUMSAT University, Japan. Please, round of applause for Prof. Kubo. Please. Yes, have a seat, please. Yeah. And the second one, we have Dr. Dinas Mananda. He is from the University of Tokyo, CSIS. His expert is also the GNSS applications, authentications, and so on. Welcome, Dr. Dinas. Round of applause for him. And I also invite Mr. Garin Nandito. He is the manager in our center, CSDA. He is also an expert in GNSS, and he's going to talk about some of our works that we've done so far in this school. Please, Mr. Garin. So, thank you very much, everyone. And besides some of the talks that they are going to deliver today, some of the tools that we probably also use or maybe not using tomorrow will also be presented to you. Maybe one or two questions before the presentations. Is that okay? All the speakers? Yeah. The first one maybe for Professor Kubo. Yeah. We have been talking about this satellite-based technology in Indonesia. Somewhere last month, we had the seminar on QZSS, and I think we learned a lot from Japan. We don't have the satellite yet in Indonesia. How far you think we could implement this in Indonesia, as we really need this satellite-based technology like GNSS and in many sectors? What do you think about that? Can we do that ourselves instead of always learning and using your own technology? Yeah.
So you mean, so do you want to launch your own satellite?
Of course.
Someday. Navigation satellite.
Yes. Yeah.
Okay. Yes. Yes, of course, it's true. It is possible. It is possible.
Mm-hmm.
But so how to answer? How to answer? Very so. Actually, I am from field of the GNSS receiver and software development.
Mm-hmm.
So which means the launching satellite is actually there is another expert in Japan. So I hope my answer is very useful for you. The Professor Nakasuga.
Yeah.
Professor Nakasuga in University of Tokyo. So we have actually co-worked with Professor Nakasuga. So he is actually the main, researcher.
Okay.
In terms of launching satellite.
Okay.
Yes, he has a big power. So of course we can introduce him to you. So I'm sorry, it is difficult for me to answer.
Okay, but
but anyway, it is possible. It is possible. And for example, Japan has launched not many satellites, maybe 4 satellites for navigation.
Yep.
It's actually very, very similar to GPS.
Yeah.
The performance is also very same. And recently, South Korea has a plan to launch the navigation satellite.
Yeah.
So
I think somewhere in 2027.
Maybe 25,
27.
Yes.
Yeah.
So the South Korean government put a lot of money into the university in South Korea. I know.
Okay.
So,
Okay.
so
we have,
maybe it's a good example
yeah.
for your country.
So it's very positive that we can do this.
Yes, 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 yes.
Thank you very much,
Thank
Prof.
you.
Kubo. And Dr. Dinesh, following these questions, I think all of the infrastructures, the main resources are also having the big potentials in Indonesia. From this perspective, from the micro part of Indonesia to the macro, yeah, what do you think about that? Is that possible for us?
Yes, I think so. But yeah, I think Indonesia should have their own system. But my personal view is not the navigation satellite,
Okay.
but the augmentation satellite, like SBAS.
Like Express.
Because Indonesia has a very huge marine, very huge marine area, so many islands, and also lots of problems in the marine, like fishing industries or illegal fishing control. That's one thing. And another one is the aviation. So marine, aviation, and then you also have a road, transport, railway and the road. So to manage all this, I think you should have your own satellite-based system. But I don't think navigation satellite system is necessary, but augmentation is necessary. That's, I think, definitely necessary.
Okay.
Because it provides better services, more robust and reliable in terms of safety and security. For example, the QGSS MADOCA-like system, or the QGSS SBAS, MSAS.
Okay.
Like the Korea is going to have their own SBAS system. New Zealand, Australia, they are going to have their own SBAS. It's already launched in New Zealand and Australia. So maybe, yeah, I think Indonesia should have this because of very huge population, lots of business opportunities.
Definitely.
I think this will generate change a lot. I think the infra.
We really need it, right?
Yes.
For those.
Because with the navigation satellite, we can have accuracy of a few meters. That we can have it. But when you need a dedicated and secure or this type of services, then you should have your own.
Yeah.
Because there are services provided by USA, Japan, Europe, and all.
Yeah.
But they guarantee in their area, not in Indonesia.
Yeah.
So that's the reason every country is now trying to have their own SBAS.
Yeah.
Like Algeria, they already announced. And Nigeria, Algeria, or maybe some South American countries. Maybe other Asian countries will come in the next few years. So I think SBAS is very important, augmentation system.
For the big country like Indonesia, I think it's
definitely
very,
necessary,
very significant. Yeah.
And that's technically not so difficult to implement.
Yeah.
You can use the existing communication satellites.
Yeah.
And I think Indonesia already has some communication satellites. So you can just use some bandwidth and broadcast the augmentation data.
Okay.
So it can be done, I think, technically rather simple.
Okay.
Yeah.
Thank you very much, Dr. Dinesh. And Mr. Garin, I think you've been conducting some of the workshops as well on GNSS. How do you see Indonesians, or especially the students, even some of the staff from other institution just now mentioned that they've been using GPS in the office and so on so far. What do you think? Are we ready for this as the main resources?
Yeah, I think we should be ready, and step by step we need to develop ourselves from GNSS, from GPS, I mean, to the GNSS infrastructure, to always develop ourselves to the better level, in the international level with the expert here. We need, but it's okay, step by step. Like Dr. Dinesh mentioned, we need to launch maybe first with the augmentation system, SBAS.
Yeah.
And step by step also next to our self navigation system.
Yeah, I think the understanding on the basic technology stuff is already there, right? So it's just like we need further development. All right, let's enter the first presentations from Dr. Dinesh. He's going to deliver his speech about introductions to the GNSS technology for beginners. Please welcome, sir. You can sit or stand. Yeah. as your convenience. Yes, you can do from here. The slide, please. IT team.
So I can also do from here.
Yes.
So where do I see the slides? Over there?
Here and the screen. Yeah.
Oh, okay. Okay, before I present it.
I think he's not very well for very long travel from Europe to Japan, Japan to Indonesia. Okay, yeah, this is more convenience, please.
Okay, so let me present about the GNSS, and this is very basic presentation. Some of you already know several things, but maybe some of you new, and maybe some of you have already seen these slides before, because I do the same slides many times. Okay. And there are so many slides, and we gave you the handout. Please check it. I will not go through all the slides, but I will talk which are more important. So, okay. So the first thing is, what is GNSS? I think now probably many of you already know Global Navigation Satellite System. So just now, Dr. Lin asked me whether Indonesia should have its own satellite system. I said not the navigation, but the augmentation satellites. So we are talking about the two different types of systems now. One is the navigation satellite system. So these are the systems that goes around the Earth to help you to navigate where you are. And there are the systems. How can I use the pointer? Oh, this one? Or mouse or sorry. So for example, there are different types of system at the moment. So you can see the GPS, GLONASS, Galileo, Beidou, QZ, and Navi. These are the navigation satellite systems from USA, Russia, Europe, China, Japan, and India. Okay. And on the right side, you will see different types of signals being transmitted. So we have a satellite, and each satellite transmits many different types of signals to do the positioning. Now you may ask, why so many signals? So if you see here, L1, so this is L1 frequency. This we call the band, L band. Okay? L1, L2, L5, and L6. And this L1 band was there from the very beginning, L1 and L2. Now we have many new signals, L5 and L6. And also the new satellites from Europe and India. So, and also China, okay, they are coming up. So all of these signals, if you see here, there are so many and too crowded actually. So they have different purpose to give you the standard accuracy, high accuracy, or more better services in difficult environment like under the trees or urban area and so on. So these are the reasons why those so many signals exist. And if you buy a receiver, so then you have to tell what type of receiver you want to buy. Then you need to know what are the meanings or what are the purpose of L1, L2, L5, and L6. Okay? And if you look here, L1 and L5 is very crowded. There are too many signals here. Okay? All the satellite systems, they provide the signal in L1 and L5 frequencies. So that's what now the manufacturers are looking at. And if you look at your Android mobile phone or iPhone, they have a GPS receiver or GNSS receiver. And many new Android receivers, some of them, they have L1 and L5 compatibility. Okay? So even your mobile phone has become a dual frequency receiver that can output high accuracy. So these are the trends to give you the high accuracy system. And these are provided by the navigation satellite systems provided by different countries. And those satellite systems they guarantee the service. So they don't say that they may stop it or like that. So they are guaranteed. That means everybody in the world, they can use freely. Of course, there are some signals that are not free, not open for general use. Some have a military purpose signal like a GPS and GLONASS. And some has a restricted signal like a Chinese satellite or Galileo. Galileo has even more different category. commercial, public regulated. They don't say military, but they call it PRS, public regulated services. That's for basically for security and defense like that, or government. And then they have a CS, commercial services. That's for the better accuracy and some guaranteed services. So if you want to have this type of systems, I think, yeah, if you want, you can launch the navigation satellite system. But that maybe, I think, it depends. Okay? You have to see the cost benefit, and it's not that easy, and not that economy is very high. But we'll see in the next slide, the other one, you see on the right, augmentation system. So this is what I said, the SBAS, okay? Satellite-based augmentation system. What it does is, you have a navigation satellite systems existing in the world now, and then they provide some sort of standard PVT, position, velocity, and time solution. That is about 10 meters is now guaranteed, you can get it. Okay? For example, if you take a receiver outside and observe, so you get accuracy of about 10 meters. But if you want to find out which satellites are being used, whether those satellites are healthy enough and all, of course, the GNSS satellites, they have all these, but to improve the accuracy a little bit, you can use SBAS to correct some of the errors that we'll see later. Some ionospheric related or some other models they provide to make it better. And also SBAS is required by ICAO, International Civil Aviation, in the airline, in the aircraft. So the modern aircraft, passenger aircraft, they have a SBAS compatible system, and it must be there for different navigation purpose. And all the standards are defined by the ICAO. So SBAS is a must in those systems. Okay. So if you have some aircrafts, if they have some level of takeoff and landing, I don't think it's practiced today, but some airports in the USA, I think they have this type of facility to do the landing based on the SBAS for better performance, probably. So anyway, SBAS is one system that you can use to improve the accuracy, and probably Indonesia government, if they want, I think they can also implement. And this is where now many countries are going towards. Okay? Like maybe some other Asian countries may also come up with the SBAS system in the near future. Probably they are discussing. And the ASEAN countries, so they have a very similar environment. So the space-related issues, I think very similar. So in the same area zone, so it may be very, very beneficial, the SBAS system. Anyway, just remember that there are navigation satellite system and there are augmentation systems. Yeah. There are two types. So these are the SBAS systems from different countries. You can see from USA, Japan, Europe, China, India, Russia, Korea, New Zealand, Nigeria, and Algeria. Okay. So they are coming up. So you may ask why they use the SBAS, because they already have a navigation satellite, because this is to improve some quality or the services of the navigation satellite system. Okay. And this is done by the communication satellites by providing some augmentation data, not the other type of revolving. Okay. So if you have a communication satellite, you can use that. And these are just to show that even with the very low cost or simple receiver, you can receive so many signals from the satellite systems. Okay, so we'll see this in detail tomorrow. So I'll skip all these slides. And this also how the satellites looks like. This is quite old slide. So actually you see more satellites than it's shown here. So these are the stations that we have from the University of Tokyo in different universities, different countries, in Jakarta, Bangkok, Manila, Kuala Lumpur, Ho Chi Minh, of course Tokyo, and also we have some other places as well. And if you observe the data for 24 hours, this is how the satellite path looks like. So, yeah. So I'll skip all these, and I will go a little bit about the Japanese. So this slide probably you have seen many times. It's a bit old as well. So QGNSS satellite was launched in 2010, September 11. Okay. but it was declared operational only in 2018. So it took almost 8 years to say that this is now fully functional and you can rely on these signals. So it took almost 8 years. It's not that easy to provide the reliable and dedicated services. But now we have so many signals, and you can see now I think there are 5 satellites, but 4 are working. But the first satellite that was launched in 2010 is already replaced by 1R. You can see on the right, the 1R, that is a replacement for the first satellite. And there are so many signals. So QG, Japanese satellite, is very crowded actually with many different types of signals. So this gives a very good opportunity for the researchers to work with different types of signals. And I just summarize one special, I call it the special applications to summarize all the applications that you can do with the QGSS. For example, we have a very high accuracy service called the CLAS for centimeter and MADOCA for the decimeter. So that centimeter is 2 to 5, and the MADOCA is about 10 to 20 centimeter. So tomorrow we'll see the MADOCA field test. And CLAS, it is only for Japan, not outside of Japan. But now we are discussing with the BIG to provide some local correction data so that you can have something like CLAS-like services as well in Indonesia. So you'll have accuracy of maybe around 10 centimeter or better, and with a very small convergence time, means the time to give you the high accuracy. Yeah. So these are some of the high accuracy related services. And you see the DC report. So this is for the disaster. So QG has one signal called the L1S, and that signal is exactly S-bus. Yeah? So that's what I'm saying. So Indonesia can have its own system, and you can broadcast your own disaster-related information message. Yeah? It's good that you asked this question, so I can relate all examples in terms of Indonesia. For example, you have earthquake, tsunamis. So how to tell the people that there's a tsunami? Immediately. Okay? You have millions of, I think billions population. So in the affected area, maybe tens of millions of people, you have to tell immediately. The best way is a satellite, but you need to have that that system. So maybe this L1S, which is we call the DC report, but this is basically for disaster information system, early warning system.
Immediately means seconds, in seconds?
No, it will take, yes, it will take a seconds, okay, but not the real time, because you need to verify that this event occur and upload and send to the user's device.
How many seconds?
We need to see how many seconds actually that will be. It will be several seconds.
Okay.
Yeah. Because from the control, the disaster control or government, they have to send to the satellite station and then upload and download. Download doesn't take much time. Yeah. But all this communication between the disaster to the satellite will take time. So download is just maybe within I don't know, maybe just a few seconds, 1 or 2 seconds. But it will be much faster than other media, I think. Yeah. So this type of things are very important in terms of safety or security, not only disaster, but other security related, like border control in the sea, in the marine. Land is easy, but marine is difficult. Yeah, you can't put, there's no boundary there. It's virtual, so you need to see how your border is being encroached or controlled or managed. So I think that's very useful. So I will skip all this. So these are the how many satellites and the launch plan. So okay. Also, some advantage of QGSS is because of its design. It's designed for service in Japan, because it has a very high-rise building. So if you have a very high-rise buildings, other satellites you don't see so many, because it's blocked by the buildings. So that's the reason why QGSS was launched by Japan. Okay. In Japan also, in the very beginning, they have a lot of questions why QGSS is necessary. and just a few satellites. So what's the meaning? But the reason was that because it's visible above your head for 8 hours. Its elevation is 70 to 90 degrees, so you can have a better positioning even in the high-rise building. That was one of the reasons. And also, while designing this, so many ideas came up, and they came up with the high accuracy services. Okay, this is launch schedule. So, any questions so far?
Yeah. Any questions from the floor? That 10 to 20 centimeters just now. Are we still working in centimeters accuracy, or we can go to millimeters? Because I think some of them were asking just now.
With the PPP, you can have like a PPP, you can maybe, but do you really need millimeter? Except the geodetic, okay?
Yeah, they are working on geodetics, like
But
the lump subsidence.
Yeah, for those you have other techniques like RTK and PPP, yeah, long-term observation you can go. But when we are looking at the mass market applications and the business,
Okay.
so because once you launch the satellite, you should benefit the people and the mass market, and it should have its own business. People should use it. So if you say it's only millimeter, that will be, I don't think many people need that. And also you see the millimeter is not easy. But you have antenna this big. With this big antenna, how can you give a millimeter accuracy? It needs a lot of processing. So lots of things have to be done. So you really need the infra. So CLAS accuracy is, I think, good enough for 10 centimeter, 5 centimeter, because that is actually for like autonomous driving. You need a lane level accuracy.
Yeah.
So lane level accuracy is, I think they said it's 10 centimeter, I think, plus minus 10. That's about 20 centimeter, because they just need to know whether the car is on this lane and that lane, or whether the car is very near to another car. So that gap may be 10 centimeter. So the accuracy must be maintained at that level.
Like the land subsidence in Jakarta, we have around 2 centimeters to 5 centimeters. So within the 5 centimeters, would it be possible?
Yeah, I think so, because even if the accuracy is 10 centimeters, so what you need to know is the rate of change.
Okay.
Not the absolute value. So if you are continuously monitoring it, so there's lots of noise, and it's the data is very noisy actually. So you'll be doing filtering and all this processing. And if you look at the rate of change for a long period, I think you can do it. And this is what they are doing now. So then they say, okay, our computation is accurate within a few millimeters of standard deviation. They have always the error value. And that's possible with the current measurement technique. This has been done by GPS alone for so many years. So with so many GNSS possible. But we are talking just a single point observation. When I'm driving, like I'm driving with this receiver on the car, and I want to have a 10 centimeter, and that's very challenging. And you don't need a millimeter because it's like this, huh? So 10 centimeter is very difficult, even 10 centimeter, but now it's possible.
Okay. Other questions from the floor? Or maybe you can. Okay, one question. Please, committee.
Thank you. My name is Karno from Faculty Mathematics and Science. I want to ask you about MADOCA protocol via internet. So is it protocol is available for public, or there is restricted to access it? And where we can get technical detail about this protocol? Thank you.
Okay. Sorry, yes, compact SSR. So okay. Later I will give you the reference document. So you can check the QGIS homepage, and there is a technical document where you can download. We call the IES document, interface specification. So you need to download that document from QGIS homepage, and it tells you everything. How the MADOCA correction data is broadcasted from the satellite. And it's like a navigation message that's 2000 bits. And within that, there are the correction data in the compact SSR format. So we need to know how to read and decode that. But it's all given there, but there are softwares or APIs given now. So you can use. If you want to have your own system development, you need to use, you can use those APIs. But the link, the document is available, very detailed document. For MADOCA as well as SILAS. And all the satellite system, not only for QGIS. You can get a similar document for GPS, Galileo, Beidou. Everybody must publish those documents. Otherwise, manufacturers, they don't know how to make a receiver. So all these protocol interface details, how to read the data. So everything is given. Yeah.
Okay.
Any other thing?
You might contact him later after the breaks. Yes, we can continue to the slide, probably.
Okay, so I don't know how much time we have, but
that's why we can continue with the slides.
Okay, so I don't know whether I should do this now or not, but this is more technical. How much time do we have? Because
you have 10 minutes left.
10 minutes.
Yeah.
So let me skip all these technical parts. Okay. So this we'll also discuss maybe sometime tomorrow. But okay. So some basic things we should know when we do the survey. So basically, all these GNSS satellites, they transmit a special signal. Okay? And the special signal means it has a code, carrier, and navigation data. So these are the three signals: code, carrier, and navigation data. So this code helps you to compute the distance between the satellite and the receiver. So when the satellite transmits the signal, I think I have another slide. No. Sorry. So when satellites transmit the signal, the receiver is generating the similar replica signal in the receiver and is trying to correlate the incoming signal and the self-generated signal. Okay. But there are different types of error. The receiver has a clock, which also has an error, and also the receiver it doesn't know it. So we don't know the receiver position that we need to solve. For example, the X0, Y0, Z0, this is the receiver's position. But in order to solve that, we need to know the distance between the satellite and the receiver. And that is computed using the measurement of these signals. And this is basically done by the code phrase, we call the PIN code. And in order to do that, every satellite's position data has to be available. And that position data is called the ephemeris data. So the satellite is telling you its position at time t, at that time, and its satellite is moving. Okay. So the satellite's position is all the time changing. But satellite just provide you ephemeris data at time t, and based on that, you can then compute mathematically what is the position of the satellite at that time. And if you know the satellite's position and the distance between the satellite and the receiver, you can compute the receiver's position data. So this is a very simple mathematics, but all this signal demodulation makes it complex, and also some other errors, clock error and other atmospheric errors, I mean the ionospheric errors, tropospheric errors. So all these have to be solved. So we don't go in this type of things, all the technical details, but we just show you the concept and where the errors are coming from. So you saw some of the error sources coming from the satellite here. We say that satellite orbit error, that's error in the ephemeris data, and satellite clock error. And then you have the ionospheric delay, because when the signals comes from the space to your receiver, so the ionosphere in the space cause some delay to the signal. So your travel time will change than the real one. So that has to be adjusted. And also some tropospheric delay, that's water vapor in the sky. So all this has to be corrected to have a high accuracy. So when we are saying 10 centimeter, 20 centimeter, or millimeter, means that we need to remove all these errors. And there are different techniques to remove these errors. So this is what we'll do tomorrow. RTK, there's the standard process so far now. And then we have a MADOCA PPP or standard PPP. So all these techniques will help you to remove or model some of these errors and have a high accuracy. Okay. So this is what we'll do tomorrow. And you will see if you don't remove these errors, your accuracy will be 10 meters, 5 meters. If you do S-bus, accuracy will be 1 to 3 meter. If you do RTK, accuracy will be few centimeter. If you do MADOCA PPP, accuracy will be 20 centimeter, like that. So this we'll see tomorrow. Okay. So these errors are coming from the satellites and other from the ionospheric and tropospheric. So all these have to be removed. So I will skip. Okay, so this is what I was talking. So if you don't do any correction, those are the red dots. Okay? That gives you accuracy of a mean of 5 meters, like that. But when you do the DGPS or S-bus, you will get the blue dots. So you'll have accuracy of 1 to 3 meters. And when you do the RTK or PPP, you get the centimeter level accuracy. So this we'll see tomorrow. You will log the data yourself. And without doing any error correction, you will see the red data. Then you do the DGPS or S-bus, you see the blue. And if you do the PPP or RTK, you will see the green. Okay? So this is the purpose of tomorrow. So if you log the data yourself and if you see the errors, then you will understand how you can improve. And the reason why you should have a S-bus, probably you can go to all these blue dots. Okay.
The blue one.
Yeah. So these are some errors that we can remove. That's why you can go from red to blue to the green one. Okay. So this one, okay, I will show you some of the slides. So how to remove these errors? So the traditional way is you have a base station, a differential observation. You keep a base station at a known point because you know that point already. That means you know now all the measurement errors there. And then you can model those errors to correct the errors in the field that we call the rover. So in Indonesia, I think there are many base stations like this. Also, they call CORS, continuous observation. So I don't know, but to cover the whole Indonesia, if you want to give a centimeter level accuracy, you may need thousands. I don't know how many thousands you need. You have so many islands, and those islands don't have electricity, no communication. So you see, if you want to do real time, you have to send the correction data in the real time as well. So that you need some radio link, okay, or the mobile phone. But if you don't have a mobile, you can't do the correction. So these are some difficulties for this type of a system. But this is the traditional way, which gives you very high accuracy. And there's a limitation that you can do this. You can go maybe around 30 or 40 kilometer at the max.
Radius.
Yeah.
Okay.
So if you go beyond that, the condition in the ionospheric over the base and rover may be different. So the accuracy degrades. You can't keep centimeter. And you are talking millimeter, and that's not that easy. And the static, if you observe for several hours, so your mean will be the millimeter, I mean the standard deviation. Yeah. But so accuracy and precision, okay, so different things. So to solve that type of problem of the base station, what we can use the QGIS is MADOCA or SILAS. So here we can use MADOCA. Tomorrow we'll do the demonstration. We have this MADOCA compatible receiver, very small, low cost, and it gives you 20 centimeter accuracy. Okay. So all the correction data, it comes from the satellite itself. So this is what QGIS does. But this correction data are transmitted using L6 frequency. So I showed you in the very beginning, L1, L2, L5, L6. They have different purposes, different applications. So this L6 data broadcast MADOCA correction data as well as CLAS, and depend on the receiver. So whether that is CLAS or MADOCA compatible, it can output the position data. So tomorrow we'll see this, and you will do some field survey, and you don't need the base station. But if we have a base station, we'll also do the RTK. We have here one, so let's see how we can do RTK and PPP and compare.
Sorry, before I miss this part, you have the low-cost receiver of GNSS. Can we have low-cost base stations? Because we need many to cover big area of Indonesia.
Yeah,
we have one actually in the rooftop of this building.
Yeah, the one we have is it's quite expensive.
Yeah.
But we also have the same idea of using the low-cost base station. We can use the same receiver and the Raspberry Pi connect and make it a base. But our field survey, maybe the coverage is small area, 5 kilometer or 10 kilometer like that. I think within 5 or 10, we need to see this.
So it's possible to have the low-cost base station, but the radius would be different.
Maybe
coverage.
I think around 10 kilometer.
10 kilometers.
Max, yeah.
Okay. Okay.
But I think it's okay, 10 kilometer. Because 10 kilometer radius is quite big. Or even 5 kilometer is quite big. Like if you are doing the field survey, like if you have some construction going on, like you have to do some road network, so you can deploy such your temporary base stations.
All right.
You don't need this for all the time for several years working. So I think low cost base station as a temporary unit is very useful.
Okay. Okay.
So I
next.
think that's all. Maybe those are the important. Okay, data formats. So let's do this tomorrow when we do the exercise. And please check the handout. I think I will stop here. So from now is data format, coordinate systems, and some examples. Okay.
All right.
So and examples, I have another presentation later, so I'll show you again.
Yeah, sure, sure.
So with this, I will stop here.
All right. Thank you very much, Dr. Dinesh. Please round of applause for Dr. Dinesh. And the second one, we are going to hear the speech from Prof. Kubo. He's going to talk about the GNSS applications. Please. Slide, please. The second slide.
Oh, yes, thank you. Yes. So I am going to talk about a little bit advanced compared with the before Dr. Dinesh talks. So he mentioned about the basics of GNSS, and I'm going to introduce a little bit advanced GNSS technology. So so one question from audience. So how to get L6 MADOCA data by ourselves. So if you want to do that, so probably you need to understand the okay, yes, so it's okay. I see. So you need to understand the GNSS receiver technology. And yes, I put some frequent questions. Frequent questions about the GNSS technology. And also I am going to introduce Starlink and LEO. LEO is low Earth orbit satellite positioning. And finally, I will introduce performance of smartphone GNSS. So as you can see, this is a receiver inside of the receiver. So here is antenna, GPS antenna, and here is a front end. So probably you don't have to care about this front end. And here is signal acquisition and signal tracking. Then you will decode navigation data, and you will get a measurement measurement is carrier phase and shield range measurement between satellite and receiver. And finally, you will get a position. You will have positioning solutions. So which means you need to input the software, positioning software. For example, RTK lib. So maybe some of you has heard of that. RTK lib is an open source positioning software. RTK lib is actually only here. Only here. This is actually this includes everything, GNSS receiver, but the RTK lib is only here. Okay, and after positioning, you will get latitude, longitude, height. Okay, LLH, and the position you will get position, and based on these positions, you have many applications using GNSS. It's tremendous. It's many applications. So if you want to do decode the MADOCA satellite data by yourself, you need to understand here. Okay. So before I talk about the GNSS receiver, so there are two types of, maybe we can separate survey grade receiver and the low cost receivers. So survey grade receivers is like TrimBlue and the Topcom. And the low cost receivers is like U-Blocks, and more cheaper one is smartphone. So actually, compared, so this table summarizes the difference between survey grade receiver and low cost receiver. Actually, there is not so big difference currently. Currently, there is no big difference.
Is it considered high end for the $5,000? Is it
possible? Yeah, $5,000. This is just my opinion. Yeah, $5,000 is Novatel. Do you know Novatel? Have you Novatel?
Yeah.
Novatel is we can purchase $5,000. Yes.
Okay.
US dollar.
US dollar.
US dollar. $5,000.
Not rupiah.
No rupiah. Yes. Yeah.
So many zero
Yeah,
after.
of course.
Yeah.
Yes. It's
Okay.
but so recently I ordered it alloy, TrimBlue alloy.
Yeah.
Maybe some of you knows TrimBlue alloy. This is the next generation after Net R9, TrimBlue alloy. So alloy was $10,000.
Okay.
$10,000. It's still very expensive. So, but anyway, so low cost receivers. So Dr. Dinesh already mentioned low cost receivers. U-Blocks it's $100, $200, and there are some other manufacturers to produce low cost receivers. But as you can see, so RTK is maybe 20, 30 kilometers is okay. Open sky, it's okay. It's perfect. RTK perfect. Even using low cost receiver, perfect. And over 30 kilometers is almost okay. Until 50 or 60 kilometers, the semi-urban, dense urban, and accuracy in RTK is almost same. The difference is in maybe multipass mitigations. Multipass mitigations in survey grade receivers is quite good, and the low cost receivers is so-so. But performance is almost same. So please keep in mind. Yes. So if you want to study inside the GNSS receiver, probably software GNSS receiver very suitable. So if you are interested in receiver inside of the receiver, software GNSS receiver will be suitable. So actually there are some very suitable websites, and we personally generated this website GNSS Learning, and we have had a project to teach GNSS receiver to the students in Japan. So our team has continued 3 years. 3 years we have taught to the students to understand the inside of the GNSS receivers. So the result and the software and the almost all informations you can get from this website. I hope it will help you. Yes.
Open access.
Yes, you can access. And if you want to do decode, if you want to receive the MADOCA L6 signal by yourself, so this website is quite good. Because one of my students doing the same things.
Yeah.
Yeah. Do the same things. Yes. まあ、高須さんなんだけどね。So if you want to study in positioning software, as I already mentioned, RTK is very good, and also the RTK Explorer. So this is the American guy developed the RTK Explorer. So this was also very good, a little bit better than RTK. So I have talked with the guy who developed the RTK Explorer. He was a very nice guy. He was maybe 55 or 60 years old. Yes, yes. He's a very nice guy. And maybe you can contact directly to him. Yes, yes. So these two software are very popular. And yeah, so Dr. Lee, you went to Finland. Finland is actually Finland Technology University. Do you know Finland?
Technology?
Yeah, it's okay. So in Finland, actually, two very useful software available.
Okay.
Yeah, I'm sorry, I cannot remember the name of the university, but anyway, Finland is very famous in terms of positioning software as well as software receiver.
Okay.
Yes. Yeah, University of
Vasa.
Yes. FGI, yes. Yeah. So applications, it is impossible to cover a lot of applications because too many applications, too many. So in Japan, for example, because the mobile phone towers, mobile phone providers, they always use GPS to synchronize the time. So it's many. So which means the GNSS already penetrated into the infrastructures. Very important infrastructures, GNSS is used. So that's why maybe Dr. Dinesh will talk about spoofing and interference. So there is another big issues in GNSS because GNSS is very weak. GNSS, the signal strength of the GNSS is very weak. So it means that it is easy to jam. It is easy to jam GNSS signal. So we have to cope with these big issues. Yes,
to
because
hijack.
Yeah. Because
To
GNSS
hijack.
is already available
Yeah.
in infrastructures. Sorry. Yes. It's okay. Yeah, I will skip this one. Yeah. Many signal. And sorry, I will skip this one. So this is Navipedia from ESA. Yeah. So I put two fish sky view of GNSS. So maybe 2 days ago, I just checked the Trimble website, Trimble Planner. So the left figure shows the fish sky view of the Tokyo, and the right picture shows the fish sky view in Jakarta. So yeah, you can see. Yeah, Jakarta is very good. Jakarta is very good to receive multi GNSS because yellow color is Beidou Chinese Beidou system. Yeah, and actually in Japan, so north part there is no satellite, no spy, because the inclination angle is 55 degrees for Galileo, GPS, and the QGSS. GLONASS is maybe 60 degrees. But inclination angle is 60 degrees means over 60 degrees there is no satellite. Okay? Okay. So that's why in Japan, so north part there is no satellite. We cannot see the north direction. We cannot see the satellite in north direction. Anyway, so Jakarta is quite good. It's quite good. Yes. So maybe too many navigation satellite you already have. So that's why Dr. Nilesh talked about navigation satellite. Launching navigation satellite is maybe you need to discuss this very carefully But like S-bus, communications using communication satellite to transmit the collection data, so it will be useful because you have a lot of satellite, you have a lot of navigation satellite. Not that you have, so you can receive. So you can receive.
So what do you mean good? Is it the numbers or
Yeah,
the
number of
Okay.
visible satellites is probably the best location.
Okay.
Yes, in Indonesia, Malaysia, Singapore.
Singapore.
Yeah, Thailand also is very good location because of the many satellites from Beidou.
Okay.
Beidou, yes. So actually in Japan, so we will launch another 3 satellite next year. In addition, another 4 satellite we will launch. So government has already decided. So which means in total 11 satellite we have. So 11 satellite means we can get our position using own satellite, only QGSS satellite. Okay, because until today, so we rely on GPS plus QGSS, always GPS plus QGSS.
Yeah.
But the 11 satellite is available. We can use only QGSS to produce our position. Okay. So the motivations, unfortunately, motivations from Japanese government is not from our side. Probably motivation is from national security.
What is it? What
Yeah,
are the
because
facts?
they want to own their own navigation system. Because some, I'm not sure if the GPS signal is not available, so we only use QGSS.
Okay.
Yes, so that's why they decided. They decided means they plan to pay money. They plan to use their tax, okay, for people. So they need a very, big motivation. Yes. Unfortunately, this is not from consumer side. This is from government, actually. So which means national defense in Japan, they can use only QGSS to produce their own positions. But now, no. We have to use the GPS receiver. We have to use, But maybe the next few years later, we can use only QGSS.
Okay.
So they, the Japanese government and the U.S. government, they have talked. They have had a kind of the solution. Okay. Yes. Okay, so I will skip this one. So SRAS, SHIRAS, MADOCA PPP. SHIRAS is very, this 2018. Yes. 2000. Okay, I will skip. Yeah, so this slide shows the relationships between accuracy and practicality. As you know, single point positioning is already available in your smartphone. Okay, smartphone uses basically single point positioning and several meters. It is enough for you. Several meters. And the RTK is also very popular in Japan. How about Indonesia? Jakarta, Indonesia, popular, very popular.
Kind of.
RTK is very popular in Japan because surveyors always has used RTK.
Yeah.
Okay, so the new technology is PPP RTK and the MADOCA PPP. So tomorrow, Dr. Dinesh will demonstrate PPP. And S-bus also. S-bus is actually for aircraft navigation, and S-bus is for the land users. But compared with single point positioning and RTK, so the practicality is quite high. RTK, but the S-bus PPP RTK is so-so. PPP is not so good because PPP we have to wait for 15-20 minutes. So this is a very big issue.
Yeah.
So we would like to improve. Convergence to shorten the convergence time. Okay.
To
so
what?
now, very good.
To shorten it from 20 minutes to what?
To 20 minutes to, 5 minutes, 3 minutes.
but not seconds.
Yeah, yeah. So not sorry, not second. So, so PPP RTK is maybe less than 10 seconds. Less than 10 seconds. Yeah.
Yeah.
Switch on is 1 minute, but after that less than 10 seconds, 20 seconds. Yes. Okay. Anyway, so そんなとこかな. Okay, so if you want to see the difference between PPP RTK and PPP and RTK and SRAS, so you can check the performance because we have continued to monitor these 4 collection services on the rooftop of our building in Tokyo. Okay, which collections should we use? So RTK and the SKSG and the MADOCA PPP, I just put. So it depends on the applications. If your application, you can wait for like 10 seconds and power on 1 minute, you can wait on 10 seconds, you can use PPP RTK and you can get several centimeters, 2-3 centimeters. But if you can wait for 20-30 minutes, it is okay. MADOCA PPP is okay. Yes. Yes, still 5 to 10 centimeters. Yes. So the big difference between RTK and PPP RTK, MADOCA PPP is, you don't need a base station. You don't need a base station. And collection data through the satellite. Okay. So do we have to use multi-GNSS constellations? Yes. Yes. So if you are in completely open sky area like rooftop, so maybe GPS is okay. Only GPS is okay. But in real environment, there are some obstacles. Of course, these buildings, trees, and overpasses, many, in reality. So there are many obstacles. So that's why I recommend you to use multi-GNSS. And do we have to use multi-frequency? Yeah, multi-frequency is, if you need precise position, yes. You can compensate ionosphere errors. And also if you have dual frequency, you have instant RTK, 1 second, 2 second centimeter accuracy you have. So recently, so this is a paper from the Texas, University of Texas, and the professor Todd, he is very popular in this Leo signal structure of the Starlink KU band downlink. So I'm not sure about the center frequency of Starlink, maybe 5 gigahertz, maybe 10 gigahertz. I'm not sure, maybe 10 gigahertz. So his team used Starlink signal for navigation. And it seems to be Starlink satellite to GPS. It seems to be okay. It seems to be practical. But Elon Musk refuses to cooperate because, but his team research makes it possible. So if you are interested in this, signal structure of the Starlink, you can read this paper. And next one is IMU. So Dr. Parkinson's talk. So there is expectations that technological innovations in inertial sensors, inertial sensor, accelerometer and a gyroscope. So if you have the absolute positions and if you have very precise inertial sensors like gyro sensors and accelerometers, so you can predict your position very accurately. So GNSS and IMU they can help each other. Okay, they can help each other. Okay, so this is quite important. Okay. But I totally agree with Dr. Parkinson's talk because he mentioned about the United States is trying to use only inertial sensors to achieve very accurate positions, 1 meter, 2 meters. But unfortunately, it is impossible. It is impossible. Because if you have, it's very big, ring laser gyro, it's very much more expensive. So you have ring laser gyro, maybe you can do that, but it is not present now. So anyway, so GPS, GNSS, and IMU, they can help each other. Yes, they can help each other. So Starlink, yeah. Do you know Starlink? Starlink? You know? Have you heard of that?
Starlink.
Starlink. Yeah.
Of course.
Starlink is available in Japan. Maybe Indonesia is also available. And this is here you can see antenna. Antenna is like this. Right? If you put antenna, so you can maybe you can have like 70 megabps or 60 megabps. This is similar to maybe probably here. So Wi-Fi connections, and yeah, it is useful, and it's only $500 US dollars, and every month I paid $50 per month. $50 per month. Yes. Okay, so we did 70-kilometer baseline RTK. This is the real results. This is the real results between 70 kilometers RTK. Okay, 70 kilometers means here is the antenna, the base station. Base station is whichever is okay. This is Tokyo, our campus. This is our how to say, just a training center. Training center of the TUMSAT, and the 70 kilometers baseline. And so here is RTK result. So you can get 10 centimeters accuracy. 10 centimeters accuracy. 10 centimeters. 70 kilometers. Okay. So we have continued this monitoring maybe from December last year to now, and it's same. It's same. It's same. So sometimes due to the ionosphere scintillations, we fixed rate is quite decreased, maybe 70 or 60%, but mostly 100%. Mostly one. Okay. So background of Leo. Yeah, I will skip this one. Leo positioning. So this is the master. Sorry, this is the master thesis. How to say? Master course thesis. Sorry. Do you know? Okay. So here is GPS. So Meo GPS, and here is Leo, low Earth orbit. Compared with GPS, the Leo satellite is very high frequency. Doppler frequency is quite high because it's very close. Very close. GPS is 20,000 kilometers, and the Leo satellite is less than 1,000 kilometers. So that's why speed is very speedy, and the Doppler frequency is quite high. So which means so here is the in case of the, so if you set up a Iridium satellite, so Doppler distributions, and like this, Doppler distributions like this. So this means that if you are in here, so your Doppler frequency is this color. Okay, if you are in here, your Doppler frequency is this color. So which means if you know the position of the Leo satellite, and if you receive the if you track the Doppler frequency, and you know the Doppler frequency, you will know your position. This is very beginning of the navigation, satellite navigation. So before GPS, United States uses this technology, Doppler positioning. Very basic. And if you have two Leo satellite, for example, two Iridium satellite. So yeah, this is the result. So result is about 200 or 100 meters accuracy you have. So it is enough for the SIP. It will be enough for the SIP. Yes. Okay. Yes. Next. Yeah, performance of smartphone GNSS. Yeah, smartphone. So do you know Google smartphone decimeter challenge? Have you heard of that? Google smartphone challenge? So this year Google announced, so they started 2024. So they started again Google smartphone decimeter challenge. So the target accuracy is decimeter, which means less than 1 meter. So the many participants joined this challenge, And if you got the winner, if you got the first place, so the $7,000, 7,000 US dollars you got. And you will be invited into the United States to join this conference, ION conference. Yes. Anyway, so less than 1 meters, the 2023, so there are maybe 50 data set from Google smartphone, Google Pixel, and maybe Google Pixel. Sorry, I forgot the name of Xiaomi smartphone. Maybe 5 types of smartphone. So you need to analyze by yourself. So in that case, what kind of software do you use? RTK Lib or RTK Lib Explorer or your own software? Actually, the developer of the RTK Lib Explorer, he got fourth place in this smartphone challenge. So maybe you are not interested in this challenge, but anyway, okay. So you don't look like it's okay. Anyway, so smartphone, yeah. Okay, here is Pixel 6. So the rooftop, this is rooftop of a building, and I put the smartphone here, and here is uBlox F9P base station. Oh, always we got the data base station because base station here, and here is Pixel 6, and you can see Pixel 6. Okay, here is four corner. Okay, here you can see the centimeter level. You see centimeter level accuracy from the smartphone. So you need to get to the measurement data, carrier phase and code phase through this smartphone, and you will analyze by yourself using your own software. Okay. Yes, it is possible. Now it is possible and amazing. So Pixel 6, it is easy to fix ambiguity. This is Pixel 5. Okay. I bring Pixel 6. Maybe I can show you tomorrow. So yeah, okay. I skip. So this is pedestrian on the ground. It's very open sky area, so that's why we can get fixed positions. Okay, thank you so much.
Thank you very much,
Thank you
Professor
so
Kubo.
much.
And maybe one question from the floor. Is there any?
Any question?
Please.
Please. Yes.
Yeah, it's from our MC. You can use the mic, please. You have the mic?
Well, you said that building and trees might be an obstacle for GNSS to receive.
Trees.
Yeah. So how is the maximum height of the obstacle that can be reached for that?
Maximum height.
Yeah, like maximum height.
Maximum height.
Because we have a lot of trees and buildings here. So.
I see. Yes. So maximum height. I know. In downtown area in Jakarta, so you have many high-rise buildings. So maybe 100 meters, 200 meters, 300 meters. It's same as Tokyo, actually, and you also have trees. So yeah, higher buildings is actually not good for GNSS. You know, this is not good. But if you can receive the line of sight, direct signal from the satellite, at least maybe 5 or 6 satellites, you can see it is okay. You don't need to mind the high-rise buildings. Even you have many high-rise buildings, at least maybe 5 or 6 satellites, you will see it is okay. So for example, back to
The slide, please. Slide, please.
Could you, sorry. to, sorry. Thank you so much. Thank you so much. And you see, you see here, here is your fish eye. This is a fish eye view. So if you are in the narrow street and high-rise buildings, both sides, and probably you can like that. You can see only here, only here. But maybe you can see more than 10 satellites, even if you are on the very high-rise building. So which means it is possible to have a centimeter accuracy. It is possible. So the higher buildings is not good for GNSS, but most important thing is how many satellites you can receive. Open sky area is 50, more than 50 satellites, and only like narrow street, maybe you can get 6, 7, 8 satellites. Still, you can have a centimeter accuracy. Yes.
Yeah, it's very interesting. I think it's not only the height of the building matters. I think the distance between the buildings.
Yes.
In urban studies, we call it sky view factors.
Yes.
The openness to the sky.
Yes.
How clear is the sky from the fish view?
Yes.
So you would not only the height of the building, but also the distance between buildings.
Yes.
Because
Yes.
the high density cities,
Yes.
it's not only talking about the high-rise buildings, but how are they close to each other between the buildings? So I think we also need to do some kind of research on this. The quality of the signals for certain angles of the sky view factors.
Yes. Maybe Google Map. Maybe Google Map you can use. You can simulate your how many satellites you can see. Google Map can be used for your simulations. Because
Okay.
Google Map you can you have 3D buildings model in Google Map. So
Real time, right?
Yes, you can use.
Okay.
So yeah, I can introduce good researcher in terms of this 3D map and 3D. Yes, I can introduce later.
Yeah, and we can also ask the students to research on that from the urban studies. Thank you very much. Any more questions from the floor to Professor Kubo? From the students? No? In that case, thank you very much, Prof. Kubo, for the very good speech. Please a round of applause for Prof. Kubo. And we're supposed to have 10 minutes break. But we are behind the schedule. Do you need the break, or we can go on with the agenda, but you can also enjoy the coffee at the back there. And I think you also have your meals with you. So is that okay to continue? Yes? Okay. Okay. Then we continue to the third talk, the applications of GNSS and its examples. How is working for the urban environment, for the difficult environment in the urban area, how is working. So let's see that from both of them, from Dr. Dinet and Prof. Kubo. Yeah, please, who is going to present first?
We will have a break now.
No, no, they said just continue.
I could be. Let's have a break.
Oh, okay. He said that we need 5 minutes break. Okay, so after 5 minutes, we continue with the talk. Thank you very much.
Very good. Yeah, I if I bring the support, I don't know what. But maybe okay. Maybe okay. You don't. You bring from the hotel? Yeah, the support. Yeah, in hotel I don't drink. I don't drink the tap water because I always choose tap water. Yes. In Indonesia, so you usually use yes. The bigger one. Bigger.
Dari bigger one.
The quality of the tap water is not so good. Not so good. Not so good. Really? Even local people do not. But in Tokyo, we drink tap water every day, every day.
But the water is ready filtered, right?
Oh, yeah.
Yeah,